So now let's talk about consistent hashing. And actually going back to our load balancer example, let's just talk about basic hashing for now. We talked about how we can balance user requests a pretty simple way using round robin, just going in order from all the servers and then just cycling through all of them. Another way we briefly mentioned, we can actually use hashing to balance the requests to the servers. In this case, we have 3 servers, and let's say we want to hash based on the user's IP address. Like we have to take user requests and hash them in such a way that they land at some server. And an IP address is some integer value. We're going to oversimplify this. Let's say one person's IP address is 6. So we can take that IP address and mod it. This is a math function, basically taking the remainder of 6 after dividing it by the number of servers that we have. We have 3 servers. So we mod 6 by 3, we get a remainder of 0. So we know that this IP address 6 should be mapped to server 0. Well, which one of these is server 0? Let's just label them like this: 0, 1, 2. So an IP address of 6 is always going to be routed to this server. And if we took an IP address of 7, we would get a remainder of 1. So it'd be routed to this server. If we took an IP address of 8, it would be routed to this server. And assuming that the IP addresses are roughly uniform, which they probably will be, we can assume that this is a pretty basic way of balancing the load between the servers. Now, one benefit of this hashing approach compared to round robin, the same user with the same IP address of 6 will always be routed to this server, even if this server is not the one with the lowest amount of traffic. But what could possibly be the benefit of this user always going to this server? Well, if our servers are REST APIs and they're stateless, then it doesn't really matter, because whether this user goes to this server or this server, it doesn't matter. The servers are identical. There's no difference between any of them. But what if each of the servers had some little Redis cache attached to it, and this is not a shared cache? I'm talking like this is a Redis in-memory cache, so that it belongs to the server. If they all had a shared cache that they were all talking to, that would be different, but each of them has their own individual cache. And let's say that these servers are not stateless. They are caching something for the users that they're getting, but this server would only be caching the requests for this user or any other users that are routed to it. And this server is never going to cache anything for user 7 because those requests don't go to this server. They go to another server. So this works with hashing. But if we were doing round robin, sometimes user 6 would end up going to this server, and then maybe we'd cache some information for them. Great. But then that same user might go to another server the next time they make a request. So then this server would check the cache. Well, I don't have anything, so I'm gonna have to reprocess all that work. But if that request had instead gone to this server, it would have already seen the data in the cache. So hashing is more suited if we want user requests to be mapped consistently, right, to the same server. We want an individual user to be mapped to the same server, because then we can do more complicated things like caching at that server level. And this is where, as you can guess, consistent hashing comes in. So while this very basic hashing approach is a good start, it doesn't solve everything actually, and I'm going to tell you why. I changed the example a little bit so that it better illustrates the point that I'm going to make right now, but functionally this doesn't change anything, because 9 modded by 3 would still be mapped to 0, 10 would be mapped to this one, 11 would be mapped to this one. And this is of course an oversimplified example. Your IP address isn't going to be such a small number. So now assume we've been taking requests and balancing them, and we've been able to take advantage of the caching because requests are mapped consistently to the same server. But a problem is going to arise when we remove one of these servers. Let's say I take server number 2 and just get rid of it. Maybe it crashed, or maybe we couldn't afford 3 servers anymore, or maybe we don't need 3 servers. Maybe 2 is enough for us to handle the remaining traffic. So what's going to happen now? Well, ideally, this user and all existing users going to this server will continue to be routed to this server, and all existing users being routed to this server will continue to do so. But all of the other users, maybe 1/3 of our users over here, will have to be routed to one of these other servers. Maybe we split them 50-50 between these two. to. That's the ideal scenario, because then all of these users still get their requests cached because they access the exact same server. It's consistent, but these users, we can't really do anything about that because this server went down. We have to move them to a different server. So that's the ideal scenario. That's what consistent hashing would actually do. But watch what's going to happen now, because we now have not 3 servers anymore, but we have 2 servers. So our hashing function is actually going to change. So now we have to mod by 2. So we take 9 modded by 2 and we get 1. So actually user 9 is not going to be here anymore, and user 10 is not going to go to server 1 anymore. They're going to go to server 0. So we basically swap these 2 guys. So user 10 will be here, user 9 will go here. User 11, it doesn't really matter which one of these they go to, as long as we do it roughly evenly for the remaining users. Maybe we had user 14 here, user 17, which in this case actually would not be distributed evenly. But continuing with this example, user 11 would be moved to server 1. So what we wanted to happen did not. In this example, the exact opposite happened. So this would be very inefficient, because now user 9 is going to go to this server. All their data that was cached on this server is now useless, and user 10 had all their data cached on this server, but now they're going to the other server. This is distributing the traffic evenly, but this is not an intelligent way of doing things. If we could do things more intelligently, like I mentioned earlier, it would be much more efficient, because then we could actually make use of the caching that we're doing. In many cases, if we didn't have a cache for each of these servers, consistent hashing would not matter. It's not always universally going to be the best solution, but in this example, it is beneficial, and it can be beneficial in a couple other examples, as we'll discuss later on. Now that we already kind of know what we're trying to accomplish with consistent hashing, let's briefly talk about how we could actually do it. We're going to focus at the high level because this can get pretty mathematical, and that's not really useful when it comes to system design. But the idea is that our servers are actually going to be placed on some type of circular space. I've shown this pretty oversimplified because each of these servers still has that 0, 1, 2 number, but in reality, this is a circle. It could actually be that this is 0 degrees, this is 120 degrees, this is 240 degrees, and that's how we take user requests and we map them somewhere onto this circle. But I'm going to be continuing to show this with an oversimplified view of 0, 1, 2, but we're going to be taking user requests, and instead of directly hashing and mapping those to a server, we're actually going to be mapping each request somewhere onto this circle using our hashing function. So we could take user 9 and map them somewhere. Let's say they go directly to this server. We take user 10 and map them to this server, and we take user 11 and map them to this server. But in reality, each of these, for example, 11 could be mapped somewhere that there is no server. It could have been mapped here or somewhere in this region. But the idea is that wherever this is mapped, we're going to go from that on the circle. We're going to keep going clockwise, and this user will be assigned to the first server or node that is on the circle going in the clockwise direction. So anything over here would be assigned to this server, anything over here would be assigned to this, anything over here would be assigned to this server. But to keep it oversimplified, let's assume that 11 just goes here. So far, this is exactly as our basic hashing algorithm was. We're distributing these requests roughly evenly across these servers. Now, the difference is going to be when we take one of these and actually remove them. Now, you might be thinking, well, if now we have 2 servers, isn't our hashing function going to change? Aren't we going to take 9 and instead mod it by 2 and mod this by 2? No, I've oversimplified this. Our hashing function is actually not going to be so simple as just taking the IP address and modding it by the number of servers that we have. Let's say that's n. It's not going to be that simple, but let's take another pretty simple algorithm. Let's say we actually were modding by a integer 360. So we were able to map each request somewhere on this circle, and we decided to intelligently place each server at a location where these would be evenly spaced, evenly distributed apart, so that each of them get a roughly even amount of requests routed to them. As you can imagine, there's a lot of math that goes on with doing this, which is why I've kept this pretty simple. But the idea is that now our hashing function is actually not going to change. 9 is still going to be routed wherever it was. Let's say it's routed exactly to this server, or it could have been routed somewhere over here and then moved over to this server, it's still the exact same. 10 is still going to be either somewhere here or exactly to this server, and all of these are still going to be routed over here. The only difference is with this region over here. All of these requests were originally being routed to this guy over here. But now, since this server doesn't even exist anymore, maybe it crashed, maybe we intentionally got rid of it, now all of the users that land over here are going to continue going clockwise until they find a server. At least our consistent hashing is going to do that on behalf of the user. And all of these users originally going to this server are now going to land at this other server. And this is really the best we can do. We want all the original users going to these two servers to remain the same, because if we have a cache on these servers, we want those users to be able to read from that cache. We don't want that cache to go to waste. So we definitely don't want to swap these guys, but all the users going to this server, well, that server crashed. Maybe its cache went away with it. So there's nothing we can really do about that anyway. Might as well take these users, move them to a new server. Ideally, we would want it to be distributed evenly. With this diagram, we can see that all of these are going to just this server. And at that point, this server will be the one handling about 2/3 of the traffic, whereas this guy will just be handling 1/3. I'm not going to go super in depth, but as you can imagine, there are solutions for this. There are optimizations we can make to minimize this amount and to evenly distribute the traffic. And while we mostly focused on what happens when we remove a server, as you can imagine, the same thing would happen as we add servers as well. We want to keep users consistently going to the same server. So what would happen if we added a new server over here? Well, all of these requests would still be routed here. All of these requests would still be routed here. All of these would still be routed here, but all of these now would go to the new server. There's not really anything we can do about that either. We could choose to route these requests still to this server. Maybe the server does have a cache that these users can use, but if we're adding a server, we probably did that for a reason. Maybe we're trying to handle a larger amount of scale. So maybe instead of just adding this server, we added a few more here, and we do those intelligently so that this gets a roughly even amount of traffic as the rest of them. Then there's not really anything we can do. At least we know that we're minimizing the amount of users that have to go to a new server. At least all of these are still going to the original server. It's just this small portion that's not. But at a high level, that's really all there is to consistent hashing. It can get a lot more complicated as you get really in depth, but at a high level, this is really all we need to know as developers, that consistent hashing is a tool in our toolkit that can help us in certain cases. We kind of talked about the popular example of doing load balancing, but only when it makes sense. If each of these servers don't need to consistently map user requests to these individual servers, consistent hashing doesn't matter. We can use a more simple approach like round robin, because that's a downside of consistent hashing. It is complex and we may not actually need it in most cases. There are other cases where it can be helpful. One example we talked about is CDNs. You can imagine that routing requests to different CDN servers, we would in some cases want to keep that consistent. So consistent hashing is also used to route requests to CDNs. It's also used heavily in databases, which we haven't talked a lot about yet, but imagine that instead of these being servers, these are actually database nodes. So we've taken our entire database and split the data up into 3 nodes, and we keep a third of our user data on this node, a third on here, and a third on there to be able to handle more traffic. So when we get a user request, we know that an individual user really needs to go to this node. This is where all their data is anyway. So routing them to this node would not be useful. Maybe all their profile information is not on this node, it's on the other node. So consistent hashing would be pretty useful in that case as well. There's another hashing algorithm that's very, very comparable to consistent hashing. It is rendezvous hashing. It's conceptually pretty similar. It tries to accomplish the same thing. In some ways, it's a bit more simple. So if you want to learn a bit about that, it could be useful, but I think consistent hashing is enough for system design interviews when it would come up. The difference between these two wouldn't really be huge in my opinion. And to quickly summarize the main components of consistent hashing, we have our hash key, which in our case was the IP address, but it could be something different. It needs to be something that can identify a user and then consistently map them to a node. IP address is a pretty easy way of doing so. We have our hash function, which would definitely not be as simple as modding the IP address. It's probably going to be some industry grade hashing function, something like SHA, which stands for Secure Hashing Algorithm. It's going to be some variation of this or some other industry grade algorithm that we don't really have to go in depth. And lastly, we have our nodes. In this case, they were servers and we were doing load balancing. They could be CDN servers, they could be database partitions or shards, but we use the general term nodes. We have a certain number of them. That number of them is changing. They could be increasing or decreasing, and that's when we need consistent hashing if we need to consistently map requests to the same node. And that really is all there is to it.